Hi and welcome to my tutorial on threads in C++. Multi-threaded programming has been practiced for a long time, but up until version 11, a C++ programmer had to resort to using some third-party library or a platform-specific API. However, today threads are part of the language. That is, there is a standard library we can include and use in our programs to write multi-threaded code. There are at least two incentives or needs when we would consider executing some parts of our program concurrently on different threads. One is to increase the speed of calculations, and the other is to separate out long-running, resource-intensive or background tasks from tasks that require short response times, such as user interface events. In this tutorial, I'm going to show you some basic and some not so basic techniques in using threads in your applications by means of a number of examples. I just note that in multi-threaded programming, one frequently encounters the problem of shared resources when at least one thread is writing to a resource, like some memory location or a file, that other threads are also using. But since this is such a large topic, it will be discussed in another tutorial, not here. Let's begin with a simple example where we execute a function a couple of times, first in series and then in parallel by running them on separate threads. Here is the function. It just prints a symbol, a character, on the standard output. One of the input parameters tells the function what symbol to print, and the other the number of times the symbol should be printed. Here is our code. If I run this little program, I get this result, which is just what I expected to get: 500 notes followed by 500 crosses. Now, how do we execute that function on different threads? The syntax is straightforward. A thread variable is declared like this, and its name is followed by the name of the function to execute and its parameters within brackets. What might catch you by surprise is that when using this syntax, the thread starts running and executing the function straight away. You stop the thread by issuing this join statement. Join will execute only after the thread finished all its work. The name join indicates that the thread joins or merges with the main thread and thus ceases to exist. Okay, so now I run this program. Surprise, surprise, the crosses and notes are all mixed up. That comes from the fact that both threads are running at the same time and grabbing the console repeatedly to print their symbols. Neither of them can hold onto the console for too long. The operating system makes sure of that. This is on the side, but my PC runs Windows, and Windows is not a true multitasking operating system. It is a task-switching system. So, although we are talking about parallel processing, it only appears to be parallel. I mean, it appears to be multitasking from the user's perspective, but actually the two threads in this example are given very brief slices of processor time and taking turns to do their work. These technicalities aside, as far as we are concerned, the two threads are executing concurrently. By the way, how many threads are in existence here? Only two? Not two, but three. There is also a so-called main thread that began running as soon as the application started. We can only kill that thread by killing the application. Now let's get the main thread do some work as well. Consider this example. Thread 1 prints notes, thread 2 prints crosses as before, then thread 1 joins the main thread, effectively disappearing. Then here is the main thread printing its symbols, which are dots. And finally, thread 2 ends here. If you look carefully, what is odd about this output is that the dots are never mixed up with the notes, they are only mixed with the crosses. This is because the join statement on thread 1 blocks the main thread. The main thread can only continue after thread 1 has done its work and joins the main thread. When the main thread starts running again and prints its symbols, thread 2 is still running, and so the crosses and the dots get mixed up. To prove that, I'll move this join statement down here after the main thread's print symbol function call and see what happens. As you can see, now they are all interleaved. Just as we can start off a thread by giving it a function to execute, we can also launch a thread with a function object. And by the way, the function the thread initially executes can of course call other functions, so any number of program statements can be executed on a thread. I thought I mentioned that just in case. So why would we use a function object instead of a function? Well, a function is just a function, but a function object is an instance of a class, such as this ball bouncer class. And the class can have member variables, which come handy when we want to store and maintain state information. Ball bouncer has a ball type and the number of bounces it should bounce. The ball type is set when the ball bouncer object is created. This is the member variable initializer. Then we can tell the ball bouncer how many times we want the ball to bounce. And finally, this is the function that bounces the ball. This function execution operator makes this object a function object and lets us use syntax like this, where in order to execute the function, we simply write the name of the object followed by the function execution operator. But I'm getting ahead of myself, because first I also need to point to this bounce count member variable, which counts and stores the actual number of bounces. So in this example, a soccer ball is created and told to bounce 7 times. A tennis ball is also created and it is to bounce 9 times. They will be bouncing concurrently on 2 different threads. The tennis ball is bouncing on thread TH and the soccer ball is bouncing on the main thread. After they've finished bouncing, the number of times the tennis ball has bounced is printed out. The function object's bounce count variable is expected to hold the number of actual bounces. You might call that historical information. I'm not interested in the bounce count of the soccer ball because it was executed on the main thread, which is still alive. Thread TH, however, is already gone. Oops, apparently the tennis ball bounced 0 times, which is clearly wrong, because we can see the T's here. So what's going on? When the new thread was launched, it received a copy of the tennis ball object, whereas here, the bounce count of the original object was printed. In order to let the thread work on the original function object, it has to be passed by reference, using this syntax. The functional standard library has to be included when ref is used. This time we get the correct result. Notice another interesting thing. Why is T printed next to S? On this line, when one thread prints its ball type, before it manages to print the end-of-line character, the other thread takes over and prints its ball type. This is a similar story as the one we saw with the notes and crosses before. Moving on to the next topic, and this is going to be a quick one, A thread can be launched with a Lambda expression as well. If you are not familiar with lambdas, I've got another video tutorial on that you are welcome to watch. When working with objects, frequently the need arises to execute one particular member function on a different thread. For example, let's say I have a ledger class with two functions. One gives me the last entry in the ledger, and another which prints a lengthy report that takes a long time to run. I, as a user, decided to print the report, and then, on second thoughts, I want to look at the last entry in the ledger. This is what happens. I have to wait and wait for that report to print before I get my last ledger entry. That's just not on. So I call the developers and tell them to do something about this. And they come up with the following solution. They execute the long-running task on a different thread. The syntax is this. The first argument is the address of the printReport function of the class. The second is a reference to the actual object we are working on, which was instantiated here. Note the difference. This is an address, and this is a reference. If I deleted this ampersand, I would get an error. If I removed this ampersand, the program would still work, it's just I would be passing a copy of the ledger object. In this case, the only difference is that passing a reference is more efficient. But as you saw earlier, if the thread made some changes to the object, and I wanted to read those changes after the thread finished execution, then I have to pass the object by reference. Here is a quick and dirty modification to illustrate that point. A word of caution: when the object is passed by reference, be careful not to modify it while the thread is still working on it in ways that would cause inconsistencies. In the examples so far, the new thread began running as soon as it was declared. This poses a problem if, say, we wanted to execute the thread only if a certain condition holds. What if the program asks for a confirmation whether or not to print the report? This example is similar to the one before, except for this additional yes or no case. The problem here is that this join blocks the execution of the main thread. So we are back to the situation we had at the beginning, namely that we have to wait for the report to finish printing before the most recent ledger entry can be retrieved. The solution is to declare a thread variable and postpone the actual creation and execution for later. If the response is yes, then a thread is created, assigned to the variable, and starts running. Because the thread variable was declared up here, it is still visible down here, outside the if statement. However, when the response was no, we don't have a running thread down here. So there is nothing to join, and that's why this test needs to be taken. A thread is only joinable if it is still running. Next topic. It's all very well that we put certain tasks on different threads and enjoy the benefits of concurrent execution, but how do we, the caller, know what the threads have done? Function objects was one solution, but it is not always appropriate to store things in the object with which the thread was started. Another fairly crude solution is to use variables that are accessible both outside and inside the thread. There are two kinds of such variables. One is a global variable, the other is a so-called thread local variable. The global variable is common to all threads, including the main thread, where it is declared. The value of the thread local variable is unique in each thread. Here I declare a lambda expression that captures these two integer variables by reference, increments their values, and prints them out. I spawn off these two threads with the same lambda. Let's see what we get. Both threads increased the same global count by 1, whereas each thread incremented its own local count. Here is a slightly more complex example. We have a lambda expression with 3 variables in its body, a local variable, a static variable, and a thread local variable. All variables are incremented and printed out. Thread 1 and thread 2 are launched with another lambda expression that captures the lambda declared here and executes it 3 times in a row. Again, if you are not familiar with lambdas and this looks cryptic, I suggest to watch my tutorial on lambda expressions. You find it on my YouTube channel. How does this look for an output? Upon each execution of the lambda, the local variable started off at 0 and got incremented by 1. The static variable was incremented at each execution of the lambda by both threads. The thread local variable was also incremented by each execution of the lambda, but only by the thread to which it belonged. The interaction of threads is a large and, I think fair to say, advanced topic when shared memory is involved, and I will do a video tutorial on that, but for now, here is an example that is more sophisticated than the ones we've looked at so far. It uses the concepts of promise and future. This is not easy to grasp, but I will try to explain it the best I can. A promise is some place where one thread can store or deposit information at another thread's request, and future is the ticket to get access to that information when it becomes available. Consider this example. But before you read the code, let me describe what goes on here. At the moment, a tennis game is being played between Djokovic and Federer. The announcer at the radio station is asking the reporter on the field for the result of the game. The reporter takes its time to answer because the game is still in progress. While waiting for the results, the announcer reads some other news. When in the future the game is over, the reporter hands over the results as promised. Now let's look at the code. A promise can be of various types. Here it is a string object I call tennis score request. This is where the radio announcer wants the results of the game to be stored. But to be able to read the results, it has to obtain a thing called future, which is a means to access the results stored in the promise. This is what happens on the second line. Tennis score result is a future variable which is initialized with the return value of the getFuture function on the promise object. Then a new thread is created, and this is where the reporter lives, so to speak. The game result function is the reporter. Tennis score request is passed to it which is a promise, and here I call it score because this is where the result of the game will be stored. The reporter waits for the game to end, then sets the value of the score. Meanwhile, at the other end, the announcer checks if the results are available. If not, then does something else, waits a little more, then checks again, and when the results are available, it reads them. It reads them by executing the get method of the future object. So this is one way for threads to communicate with each other in a structured manner. I hope this tutorial was useful. If you have questions, please ask them in the comments. Thanks for watching.